Hi, and welcome to 3.7H 2D motion and asymmetric projectiles. In this lesson, students will be able to calculate and fully describe the motion of a projectile fired at an angle landing at a different height from which it was projected, and also students will be able to calculate and fully describe the motion of an object accelerating in 2 dimensions. So there is going to be an x acceleration in some of these problems. But let's start with a projectile problem. So we got our asymmetric problem just in time for Halloween. On a dark and scary night in the quiet town of Sleepy Hollow, Ichabod Crane walks down a solitary road through the middle of the deep dark woods. Ichabod hears the hooves of a horse out in the darkness. The hoof falls get quicker and quicker, louder and louder, until the headless horseman and his ghostly steed round the turn ahead of Ichabod. Ichabod soils himself. Okay, so it says the headless horseman throws his ghastly jack-o'-lantern head at Ichabod with an initial velocity of 20 meters per second at an angle of 20 degrees above the horizontal. Ichabod dodges the head, which lands next to him 1.8 seconds later, so it hits the ground. How far above the ground was the pumpkin when it was thrown? So we'll start the same way that we normally have by drawing a diagram. There's our pumpkin, and then it's going all the way, and then it hits the ground, which, the pumpkin's over here above the ground because it's on top of the horse. So it goes downward dy, and it has an initial velocity, vi is equal to 20 meters per second at an angle of 20 degrees with the horizontal. That's the situation, and here's how we're going to do it. We're going to break the initial velocity into components by drawing in our x and y components. We'll use the shortcut method to solve for VIX and VIY. So the pumpkin is moving across pretty quickly, 18.7 meters per second, and it starts by going upward at 6.8 meters per second, but we know that's going to slow down to 0 and then speed up as it hits the ground. So we're going to solve for dy. Would you expect dy to be positive or negative? Keep that in the back of your mind. Now we're ready to set up our XY t-chart, and we'll plug in what we know. Now we don't know what the displacement in the y direction was. Before, when it was level ground, the displacement was 0, but now we're ending up going downwards, so we should get a negative displacement. The initial velocity, though, is upwards at 6.8 meters per second. We don't know what the final velocity is, but we know the acceleration is negative 9.8 meters per second squared. They tell you the time is 1.8 seconds, and we even know the horizontal velocity, 18.7 meters per second. So we could find the range if we wanted to, but they're really just saying how far above the ground was the pumpkin when it was thrown. So we have D, VI, A, and T. We want the equation without VF in it, which is this one. You substitute in your values, and you end up getting a negative answer, negative 3.56 meters. So what does that mean? That means the pumpkin was 3.56 meters above the ground when it started, and then it ended up going down in the negative direction because it was here, and then it ended up going downward towards the ground. So that's the answer there. Now, as you can see, they could have a lot of fun with this one. This was just kind of the basics because the kinematic equation, you only had to do one. But what if they asked for the maximum height? You might have to do some thinking there. What if they asked for the range? Okay, so each situation might be a little bit different, but that's kind of how you handle these asymmetric problems. Now this is going to be very different because now we're accelerating in the x direction, but we could still use our xy table. It says a spacecraft is traveling with a velocity of 4,305 meters per second along the positive x direction. Two engines are turned on for a time of 623 seconds. One engine gives the spacecraft an acceleration in the positive x direction of 0.75 meters per second squared, while the other gives it an acceleration in the positive y direction of 5.4 meters per second squared. At the end of this firing, what is the magnitude and direction of the final velocity? What is the displacement of the spacecraft? So we're going to start, we could start with a diagram. So you have your spacecraft over here and your initial velocity in the, we'll say in the x direction, Vix is equal to, you're going very fast. This is a spacecraft in space. Then, is there a y direction? No, you're just going horizontally. And then you are going to accelerate. There's this acceleration vector in the x direction. Ax is 0.75 meters per second. You're also going to start accelerating in the positive y direction. Ay is equal to 5.4 meters per second squared. Oh, I forgot my square over here. I would have gotten a point off. That's okay. So you're gonna make a path that kind of looks like this, a parabola that looks upwards like that. And let's just make the XY table and see what happens. So we have X and Y, break it up, okay? dx, and then we're gonna have Vix and VIY because we are accelerating in the x direction. That's the major difference for this type of problem. It's no longer a projectile problem. You're accelerating in both dimensions, the x and the y. So the dy side of things looks the same because we're used to accelerating in the y. Oh man, as I'm talking about x and y, I'm messing up all my subscripts. This should be VFX and that's VFY. Okay, see, people make mistakes. Totally fine. Just try to check your work as you go. Hopefully, we'll be good now. So Vix is 4,305 meters per second. VIY, it doesn't say anything about VIY. It just says it's moving along in the x direction. So that means you have zero initial velocity in the y direction. So that's a little hidden information there. Ax is 0.75 meters per second squared. And then you do start gaining some velocity in the y direction at a rate of 5.4 meters per second every second, so meters per second squared. The time is 623 seconds, and they want to know your final velocity. So we're picturing our final velocity being something like this, having an x and y component in the positive x and the positive y direction. So this is VFX and VFY. The goal is to find these two things and then do some vector addition at the end. And we can even break the displacement into components and individually find how far did it go in the x direction during this motion and how far did it go in the y direction during this acceleration. So you could like piecemeal them like that and think about them separately. Well, let's see. We have three pieces of information on either side of the XY chart, so we should be good to go. Let's find the final velocity in the y direction first, because we're kind of used to doing that. So we want the equation without d. You substitute in your values from the table, making sure to look at the x and the y. Especially with this, I would use subscripts when writing your equation. So we said we'll stick with the y side of things for now. And remember, the acceleration doesn't always have to be negative 9.8. You've been plugging in negative 9.8 for the acceleration so many times in the past few days. But remember the kinematic equation thing, we didn't start talking about negative 9.8 until like a few lessons in. We only started in unit 3 talking about negative 9.8. At this point in the year, everybody plugs in negative 9.8 automatically whenever they see an A. So just a disclaimer that it doesn't always have to be that. So at the end of this acceleration, your final velocity in the y direction is 3,364.2 meters per second. That's over here, 3,364.2. And over here, 3,364.2 meters per second. So now we can find the final velocity in the x direction very similarly using this equation. Now this is the first time that we're seeing an acceleration in both directions. Remember, this is VFX is equal to, this is 4,305, that's what they gave you in the problem, plus they're saying in the x direction it's only 0.75 meters per second squared times 623 seconds. So that's that. If you're wondering again, why was the VIY 0? It's because it's saying it's traveling with a velocity of this in the x direction, along the x direction. And it doesn't say anything about the y direction. So that's why this was 0. And this initial velocity is what was given. But that increases to 4,772.25 meters per second. I'll keep the decimals long because we're going to have some more work to do here. So over here and in our table. So if you want to, you can draw a larger vector diagram, but that gets the job across, right? We have side A and side B, so we're just going to have to do the Pythagorean theorem to find the hypotenuse. Our equation looks like that. You could either put R for the resultant or just VF. That is the final velocity that we're looking for with the X and Y components. And you get a final velocity. The resultant of those two components is 5,838.9 meters per second. And of course, since velocity is a vector, we would need to find the direction. So we'll use the inverse tangent. And you get an angle of 35.2 degrees. Okay, so now it's basically the same process to find the displacement, but obviously in these steps we're looking for dy and dx, and then we'll use those two components to find the magnitude of the displacement and the angle of the displacement. Now, think about it. Do you think that the angle of this final velocity, is that going to be the same exact angle that our displacement will be? Think about that. So to find d on both sides, we could use vi, a, and t, and use the equation without vf, which is this one. But I'll do it simultaneously for the x and the y. So we'll substitute in our values very carefully from our table with the x for the x and then the y for the y. And you get an x component of your final displacement of, I don't even know, 2827563. That's far. That is 2,827,563 meters. And then for your y, looks like you get 1,047,948.3 meters. Okay, not caring about sig figs today. That's all right though. All right, so if you wanted to like similarly set up your components, you definitely can at this point. And then you get your resultant displacement here. So there is a difference between, okay, I'm moving in this direction, you know, my velocity is pointing this way. There's a difference between where your velocity is pointing and how far you went from start to finish. Okay, so you have to, they are different physical quantities, displacement and velocity. So we'll see that it's actually a different angle. But let's do the, you know, Pythagorean theorem and all that stuff, inverse tangent. And I got kind of lazy and didn't feel like plugging in all those huge numbers, but there are the equations. I didn't plug them in, but you kind of know where we're going with that. So as you can see, like we said, the angle is different because from start to finish, your displacement is different from, okay, I might be pointing in this direction. Listen, you could be at this point right here, and your velocity could be pointing like this way. So the direction of your velocity doesn't necessarily have to correspond with the direction of your displacement. So I kind of like skipped ahead really quick, and now I would have to either redo that whole thing or just talk over this slide. So I'm going to talk over this slide. You might have noticed that those numbers were getting really long and out of control. So all I wanted to say about that was it would have been better if I used scientific notation. But since they didn't use scientific notation in the problem, which was taken from your honors textbook, I figured I'd show you what would happen if we continued with that. So whenever possible, I highly recommend using scientific notation if you have numbers that are like 1,000 or more. Yeah, because you saw how reckless it got with how long those numbers were. Just put it in scientific notation, it'll be fine. Anyway, thanks for watching and have a great day.